Okay, I've got Ramel, I've got Annabelle, I've got Ryan.
Professor, I have a different name in Zoom.
Yes, I see.
Daria.
Yes.
I cannot rename myself.
I was just looking at the name. I've got Matthew. I've got Ali. I've got Mohammed. I've got what looks like Violet. I already have Haley. Mariam. Cleon. Who am I missing? Oh, there's Serene. Andrew Baker. Andrew Moncarius. Right, so the people I'm missing, let me know if you're here. Brian, Sunel, Nicholas, Cameron, Shauna, Ashley, Nicole. Who said here?
I'm here.
Professor, I'm here.
Who's I'm? Wave your hand.
Ryan.
Shauna,
Ryan.
I'm here, Professor.
Okay, Ryan, I got you. Oh, there you go. Hey, what are you're not in your spot.
Yes, not today.
Okay. Yeah. All right, I got Shauna. And somebody else said something. Wave your hand. I got you. I got you. I got you, Ryan. Okay. All right. Thank you. So today is our last regular class. What I mean by that is next Wednesday is going to be an optional class for those of you who wish to just review for the final exam if you're taking the final exam. And of course, again, the final exam is optional. If you don't take it, it's not, your grade will remain as it is. If you do take it, it can't hurt your grade. But if the grade is higher than your lowest exam grade, I'll replace that recorded exam grade. Okay, what I mean by recorded is if you opted out of exam 2, that's not going to count as anything. Let's see.
Professor, so
Yes.
about the, you said we have time till 1st May to come in and get that extra 10 points?
That's correct for both exam 4 and exam 5. The process has to be completed by May 1st.
Okay, thank you.
Okay. Let me see. Is there a question? Chat. Okay, that's fine, Haley. Okay. Let me quickly and briefly look at the exam. I think this was probably the most difficult exam judging by the grades on here. It's important that you know this material because this upcoming exam is going to rely heavily on your skills, your integration skills. So it's all the questions I've been getting by email are mostly having to do with substitution. So this chapter, what is it, chapter 7, it's focusing on just new functions, and we're adding functions, but we're not really learning any new calculus techniques, any derivative techniques. We're using the same stuff. We're just now saying, well, now we can apply this to the new to these new functions. So we're going to complete these today. So the functions that we're adding today are going to be exponential and logarithmic functions of base other than e, and inverse trigonometric functions. And I'm going to be, through the whole period, through this whole class, I'm going to be basically going through examples. And I'd like you to try to follow me on these examples. And I'm going to ask you to log on to nearpod.com to do so. And I'll give you that in a second. Yeah, Annabelle. The examples I'm going to be doing are from the quiz, some from the homework. I want to make sure that we do and get enough practice in going through all different kinds of these problems so we get used to them. Okay, yeah, we certainly can go over the questions in the quiz. Yeah, I think when people, the things, like I said, I've been getting some emails about problems that students are finding difficult, which is normal, but it's more than usual, and they have mostly to do with substitution. That seems to be the answer to a lot of the problems is you have to substitute. And you kind of got to get used to that and practice at that, and it's a skill that you want to, that's why I want to go over as many as possible examples today for that, and through using all the problems, all the kinds of functions that are going to be on this next exam. All right. Any questions about the exams or the final exam? I don't know how many questions there will be, but the final exam is you're going to have 2 hours instead of the usual, what is it, hour and 1 hour and 45 minutes. So it's maybe a little bit longer, but it's going to cover questions from all previous exams. And you're not going to see anything new in the final exam. I'm going to go through all the exams and pick out some of the questions, not necessarily the most difficult ones, but the things that are represented. So if you're going to take the final exam, I would recommend looking at your old exams, practicing the things that you had difficulty with. I should pick the easier problems. I'll take that into consideration. It's funny. I was in my office this morning and somebody called. I answered the phone and somebody said, I'm a student who's thinking about taking your class for fall, and I want to know if you're a chill teacher. And I said, definitely not. And he said, oh, and hung up on me. So while I will take into consideration your request, it's not, not everything is going to be easy, but I expect that the final exam the problems I want to see on the final exam and I'm going to choose in the final exam are not going to be a test of your ability to do the most difficult problems. I want to see if you know how to do substitution. I want to see if you know what an extrema is. I want to see the basics. And so I want to choose problems that show me that you know how to do that. So I don't think if you do know the basics, you're not going to struggle. I'm not going to choose problems that are going to make you struggle. So hopefully they are easier. Right, no official review. The review are the other exams. Yeah, because I am not going outside those exams. I'm going to pick from within the exam. So that is the review. And like I said, next Wednesday, class is optional and it will be reviewing for the final exam. Okay. Any other questions before we start our review and preparation for this exam, for exam 5?
Professor.
Yeah.
I have a question.
Yes.
Did you say you didn't know the number of questions on exam 5 yet?
I don't.
Okay.
Could be 5, could be 30. I'm not sure. It depends on how long the problems are. All right, let's get started. Let's look at the material. And because Annabelle mentioned the quiz questions, we'll start there. We can certainly start there. Where is this? Okay, let me remind you about the derivatives and integrals for these functions. Let me share my screen.
Professor, I have a question.
Yes.
Will we have the formulas for the integrals and derivative of inverse trig function?
You've had them all along on every exam. If you actually look back, I think you've had them all along. You will certainly on this exam.
Okay.
Yeah.
On the last exam, I was searching for the formulas for the
summation. They were in that problem. They were within that problem. You just have to scroll a little bit. They were like a little lower.
What?
They were there.
I was really looking for.
What am I looking for here? Oh, give me 1 second. I'm looking for. All right. Well, let me just give you the basics here. So we have a definition that we started with for exponents and logarithms. B to the x we define as e to the x times the natural log of b, whatever base that is, and we go from there. Let me see what anything else I need. All right, and let me give you the derivatives or remind you of the derivatives. So the derivative with respect to x of b to the x is itself times the natural log of b. Okay. The derivative with respect to x of log base b of x equals 1 over the natural log of b times x. So that if you notice, they're very similar to the exponents and natural log, where we have a base e. We're having to stick in the natural log of whatever base it is. Let me see. I think that's enough to know for now. Let's see. Oh, well, the integral. Let me see. An integral of b to the x with respect to x is itself divided by the natural log of b plus c. Okay, I think that's all we need to know. So let's take a look at the quiz problems and see what's on there. And this is 7.3. So you know, and so you can maybe relax a little bit. We're not going to be taking a quiz today. I'm just going to go through sample problems. But it is a good idea to focus on these quiz questions. I tend to take a lot of questions on the exams from these. So let's look at them. Did you have any particular? Well, there's only 3 of them, so we may as well look at all of them here. Okay. So the first one is a fairly straightforward derivative. We have the function y equals 3 to the x. And as I just wrote above, and as you will have these on these formulas on the exam, but these, you really should know these. I don't know if your next teacher, if you're taking Calc 2, is going to give you a sheet. You might have to just know these. So the derivative is going to be itself 3 to the x times the natural log of the base, so natural log of 3. Oops, I wrote that messily. Natural log of 3. Okay, that's it. Any questions on that? That's the most basic. Sorry, I had the audio muted. Any questions on that? All right. Again, these are on the formula sheet that you will have on your exam. It doesn't do so much good if you really are cloudy about everything, but it will be there. So let's, yeah, Annabelle.
This may be a stupid question, but why is it not exponential of x natural logarithm of 3?
It is. What did I write? You're talking about this problem, y of 3 equals 3 to the x?
Yeah.
It says natural log of 3. Does it not look like that?
Okay, yeah, my bad.
Okay, is it my writing that you're having trouble with?
No, yeah, sorry.
Okay, this is, it's itself, like we do with the e to the x, but then we multiply it by the natural log of the base. That's it. Okay. Yeah. All right, let's look at number 2. Here I have the indefinite integral of 5 to the 3x dx. You can do this without substitution, but it's a good idea to just do it. Enough students are having difficulty with the integrals that I would suggest just automatically doing a substitution if you need to. So the substitution I would make is usually going to be an inside function, right? So an inside function here would be 3 to the x. I'm sorry, 3x. So I'm going to let u equal 3x. And then I'm going to say the differential of u is the derivative of 3x, which is 3 times the differential of x. Okay. We have a dx here, but we don't have a 3. So I'm going to divide both sides of that substitution, that equation by 3. So I have 1/3 du equals dx. Now I have a perfect substitution for my dx and for my 3x. So this is going to be equal to, well, 5, the integral of 5 to the u. So I'm substituting my 3x with u. And instead of dx, it's going to be 1/3 du. So I'm going to put the du here, and I'm going to, because the 1/3 is a constant, I'm going to move it right outside. And now I'm going to take the antiderivative, find the antiderivative here. That equals that 1/3 stays there. The antiderivative of this function, 5 to the u, if we remember, is going to be itself divided by the natural log of the base. So itself, which is 5 to the u divided by the natural log of 5 plus c. And the last thing we do is we don't want to leave it in terms of u. I should say u. We want to resubstitute in our function, so that's 3x instead of that. So our final answer here, it would be 5 to the, oops, not the u, to the 3x over 3 times natural log of 5 plus c. Bless you. There's another way to write this. This is perfectly fine, but I see that there's a different, the answer looks different in MyMathLab. However, it's going to be the same thing. So I'm going to call your attention to the fact that this 5 to the 3x can be written as 5 cubed to the x, right? We have to remember the rules of exponents. You multiply those exponents, so that would be 3x, but we can write it, separate it like that, and that would be 125 to the x in the numerator. And if we want to, we can use that property where we have the exponent of the argument inside can be made into the a numerical coefficient and do it backwards. In other words, I can take this 3 and put it up here as an exponent. So I would have the natural log of 5 cubed, which is 5 times 5 times 5, which is 125. Okay, so that's another way of writing it. Either way, one of these would be fine. The second way is just does look a little neater. Questions on that? I see a couple of questions in chat, and you're on mute. If somebody was trying to ask me a question, I've unmuted. Okay, let me see. I have a question here on the exam. Would it be sufficient to write the answer just like you wrote it without explaining any more? Well, I would like, I'm gonna look at, I do it the way I just have here. This is sufficient. What I'm writing is almost always going to be what I'm looking for on the exam. So if you're looking to see how I want to see it, look at my notes. Referring to the first one. Thank you. The first one. This one here. Oh, this is it. Through y to the 3x, 3 to the x. That's all I need. That one's a very simple problem. It's extremely straightforward. There's nothing else to say. Other questions?
Professor, I have a question. So
Yeah.
how do we know what is u? Like for this one, it's pretty simple. Okay, 3x is u. But for more complicated questions like sine x, cosine x plus something else,
Plus
how
something
do we
else?
know what is u?
Well, we'll go through a few examples. I'm not,
Okay.
if you have a specific example, that doesn't say just something else, but we'll go through a number of them. And that is the question. I mean, that's the big deal with, like I said, I've got a lot of emails about these problems, and the issue is almost always substitution. And the question is, how do I know? What do I substitute? And we'll go through a number of them today. And we'll hopefully get a feel of how we choose those. Let me
Professor?
start by continuing with the last question on the quiz here, which requires a substitution. So this one is a definite integral from 1.
Professor, you're not sharing the screen.
I'm not sharing my screen. How long have I been not sharing my
You
screen?
are sharing. Yes,
Am
I
I
sharing.
see it.
I can see.
Other people can see it,
I can't see it.
but other people can, right? Yeah, I can see it on other people's screens. You may have, maybe you minimized the window. All right.
I'm gonna go get out of the link and come back again.
Okay. All right. So this is number 3. We have the definite integral from 1 to 3e of 2 to the natural log of x over x with respect to x. And okay, so how do we approach this? It seems to me to be clear that this is a substitution problem because we don't have a formula for something with, b to the natural log of x over x. That's not just a straightforward problem. So there's going to be a substitution. So as I've said, usually the substitution is going to be an inside function, something that's inside of another function, and whose derivative is also present here, is also a factor here. So you can try out different things. Can somebody give me a suggestion about a function here that's hopefully an inside function that we could try? Okay, so natural log of x is a good guess. If it's wrong, then you try it out. And if you see that you take the derivative and it does not look at all like you're looking for, then you try something else. But it's reasonable to try natural log of x, right? That's an inside function. It's inside of the exponential function. So I would say let u equal natural log of x. And then the differential of u is going to be equal to the derivative of natural log of x, which is what?
1 over x.
1 over x, and then times
dx.
dx, right? That's what the differential means. We didn't do that chapter or section on differentials, but that's what we're doing here. And do I have that here? Is that a reasonable substitution? I do. I have
Yes.
dx over x. Okay? That's the same thing, by the way. This is the same thing as dx over x. It doesn't matter how we write it. So this is a perfect substitution. So let me do that. Let me put that in here. So this equals the integral, and I'll deal with the boundaries in a minute. Instead of 2 to the natural log of x, it's going to be 2 to the u. And instead of dx over x, it's going to be du. Okay. Now, the bounds of integration, we have 2 choices. We can either do this, find the antiderivative, and then replace the natural log of x in the substitution, and then evaluate from 1 to 3e, or we can change the bounds of integration. Yes, sorry.
How did you get this? Like,
How did I get that substitution?
yeah, no, like I understand that you pulled these out of here, but how did you end up with that?
How did I end up with 2 to the u?
2
Well-
to the u du.
Well, look at the screen. So look at the original problem, 2 to the natural log of x. We've substituted natural log of x with u. So that's where the 2 to the u comes from. The natural log of x turns to u. Look at the substitution again in blue. What do I have? What does du equal to? Well, we take the derivative of natural log of x, and it's 1 over x, dx. And so instead of writing in the upper equation dx over x, I write du. And so we now have a very simple integral. So I'm going to change the bounds of integration. I don't know what most people do. Do you when you do this, those of you who have been able to make it this far, do you change the bounds of integration, or would you prefer to reinsert the x function? Either one. You really can do either one. I think replacing the bounds of integration is easier, but maybe not. I'm used to doing that. All right, let's do that then. Okay, so I want to replace 1 and 3e. So these are x. So x equals 1, x equals 3e. But I now have to have u equals and u equals. Okay, so what I do is over on the right, I say, well, x equals 1. That means that u equals, well, I go up here to check that. That's the relationship between u and natural log of x. So when x is 1, what is u? It's the natural log of 1, which is 0. Right. So this is u is 0. So that's our lower bound of integration now. When x is 3e, what is u? U is natural log of, let's look at it a little bit, natural log of 3e. What is that? Well, remember, we can make this a little simpler, but maybe, and we can change this, use the properties of natural logs to say that this is the natural log of 3 plus the natural log of e. Okay. What is the natural log of e?
1.
1. Okay, so this is going to be the natural log of 3 plus 1. That's our new upper bound of integration. Natural log of 3 plus 1.
Professor?
Questions?
Yes, Professor, I have a question.
Sorry, I had you all on mute. Anybody was trying to
Yeah,
ask a question?
Professor, I have a question. Why did we replaced X to U? Why did it change?
Well, because we're doing a substitution up here in the thing that I boxed in red. That's our substitution to make life easier here, to make the integral easier. I substituted every natural log of X with U. So now that I made that substitution, everything has to be in terms of U instead of X. So in the original integral, when the 1 and the 3e, that stands for what X is at the beginning and at the end. But we're no longer dealing with X. We've now substituted, we're dealing with U, which is a function of X. And so we have to change those bounds. They're no longer, we want everything to be in terms of U. And so those bounds are now in terms of U. In other words, instead of saying, well, when X is 1, we don't care about X anymore. We care about U. So we substitute it in. When X is 1, then U would be 0. And so we have a new bound of integration.
Oh, okay, thank you.
Okay. It may be easier if you do this with resubstituting in your function and then see what happens. Yes, Irene.
Down here where it says ln3 plus ln e,
Uh-huh.
how did it become ln3 plus 1?
Well, ln3 is natural log of 3. What is the natural log of e? Remember, that's the exponent that when you raise e to it will give you e. That's what natural logs are. That's what logarithms are. They're exponents. You're saying, well, the base is e. So what do I have to raise that to? Blank, there's a blank here, to give us e. What does this have to be up here? 1. That's why it becomes 1. That's what a logarithm means. It's an exponent. If that was the log base 3 of 3, I would say, well, what do I have to raise 3 to? What's the exponent to get a 3? It would have to be 1 again, and whatever. That's how all logarithms work.
So
The natural log of 3 is just natural log of 3. It's some weird number that when you raise e to it, it'll give you 3. And that's an irrational number, and it's not a simple number. We leave it in that form. Okay. In other words, it would
Professor?
be e to the something would give you 3. Who knows what that is? It's, put it in the calculator, it's some strange.
Professor, I have a question.
But not for 3. Why aren't you simplifying natural log of 3 into a simpler number? Because it's not a simple number. Natural log of e is a nice number, and it equals 1. Natural log of 3, put it in your calculator. It's some crazy number. It's not solving. If you put it in your calculator, you'll get an approximation, a long decimal approximation, and that's not an exact number. The exact number is natural log of 3. Yes, in exact terms. It's that answer is exactly natural log of 3 plus 1. If you put that into the calculator, you would have to say, well, it's approximately this number. And that's in math, very often we're looking for exact numbers. We don't have to. In engineering, you end up wanting approximations, because you can't go in, and say, well, we're going to make this wall natural log of 3 meters. Nobody will respect you at all. So, but in math, we generally leave things. When I say, when you see these and the exams and on homework problems, exact answer, give an exact answer, that means you're likely going to have natural logs in there or radicals, and you're not going to put them in the calculator.
Professor, I have a question.
Was somebody asking something?
Yeah, I was asking a question.
What was your question?
So if a base is raised to a power and the power is like a constant or like 2 like variables, can we always rewrite it to like the base plus base times the power plus
Can you
same
give me a
base times
specific
a different
example,
power?
like with numbers, and I'll
So,
write it
like-
down and we'll see.
So you know how you 2 is raised to the ln of 3e. If we had
So so what you're
Three-
saying, say it again. So 2 is a base and then the exponent is natural log?
Well,
Is
in
that what
this
you're
case,
saying?
let's use like 2 raised to the 3e power or something.
2 raised to the 3e power?
Mm-hmm. So would that
That's
always
a
be
that's a
equivalent?
constant,
Mm-hmm.
and that's the answer. I mean, that there's no other way to write that. I mean, you could make an approximation of it, but and it is just a number. This is a constant, but that's it. There's no way to, well, you can write it in other ways, but I don't know if let me see. So for example, this is 3 times e, so 2 to the 3 times, let me see, plus to the e power to the e, which is 8 to the e. That's another way of writing this. But again, that's, that doesn't, that's that's an exact number. You wouldn't want to, the only other thing to do with that is put it in your calculator.
Okay.
Okay.
I understand. I think I misexplained it, but it
Okay.
was basically referring to, you know how you separated ln of 3 to plus ln of e?
You
I
mean
was
how I
referring to that.
separated natural log of 3e?
Yeah,
Yes.
my English is broken
Oh,
today,
well,
apparently.
that was a property of natural logs.
Yeah,
As
I
a
was
prop,
referring to that.
it's multiplication. It's called product to sum rule.
Mm-hmm.
Okay, so that rule says that the natural log of x times y equals the natural log of x plus the natural log of y. That's what I used here to go to this. It's a product, 3 times e. So you can also write that as the natural log of 3 plus the natural log of e. I said that right.
Understand.
Okay. These are properties of logarithms and of exponentials. You definitely want to make sure you're as familiar as you can with them because we very casually use them now. Yeah.
So you know how like down here where you changed it from ln of 3 plus ln plus e, I mean not e, ln of e
Uh-huh.
equals ln of 3 plus 1.
Uh-huh.
What if we just left it as ln of e?
Well, that's kind of like leaving an answer 3 over 1. I would say, why didn't you just write 3? It's a direct simplification. You don't want to leave it like that.
Well, would it take away points or like
A
would
little
it?
bit. Yeah, you want to, I mean, that's very, again, I would, you don't want to make that a habit, it's not simplifying.
Okay, this is
something.
what I was confused about. I just found the words to explain it.
Okay.
You know how like when you were explaining like what the natural log is and you said, oh, okay, if you want to find a natural log of 3, then okay, no, sorry. Look, you know how you explained for ln of e, that the reason why equals 1 is because if you want to find what exponent to e like
Uh-huh.
makes e,
Uh-huh.
why don't we do that for 3? Like, why is it not what exponent of 3 makes it 3? Like, why
Because
isn't
it doesn't make anything easier. 1 is a nice number. The answer, what value of e gives us 3? You would have e to the something equals 3. It's, it would be natural log of 3.
No, that's not what I'm saying. That's not what I'm saying. I'm saying like, why isn't it like like which exponent when you put it on 3 makes it 3? Why don't we use that same explanation?
Because it's not 3. It's not an exponent that we're doing. It's not 3 to something. It's e to something. This is base e. Natural log means base e. So you're starting with the base of e. There. You want to make this some e to the something equals 3. That's an irrational number. That's why we don't do it. It just happens that it works well with the e because it's just 1.
Okay, got it.
Right. This is some weird, strange number there. Okay. And an answer like what you were saying with the other way, if your answer was something like this, not square root of 2 plus square root of 4, I wouldn't want you to leave it like that. I know you know what I would want you to do, right? Right. I would say this is square root of 2 plus 2. To leave it like this says this person isn't really familiar with the basics. So you do want to write things in the simplest way possible. I am testing you for calculus, but and I'm not going to be, ruining your grade over that. But I always prefer you to simplify. All right. Are we ready to complete the problem? Okay, I realize that a lot of the issues here are with pre-calculus stuff. But you really want to have to do your best to refamiliarize yourself with all these little rules. All right, so let's do it. Let's take what is the antiderivative of 2 to the u? It's going to be on the formula sheet. It's written up above in red. Should I scroll up, or do we know what the antiderivative of 2 to the u is?
Do you want somebody to answer, or
Yeah,
it
somebody
before?
to answer.
It would be 2 to the u over the natural log of 2 plus
That's right.
c.
Right, well, right, that's it. We don't need the plus
This
c only
is
because this is a
definite.
definite integral, so we don't need that. But yeah, that's it. It's itself, but divided by the natural log of 2. Evaluated, in this case, from 0 to natural log of 3 plus 1. Yeah.
What happens to du?
Well, that's like saying when we have square root of 4, it equals 2. What happened to the square root? It's a
Wait,
kind of an operation that we're performing, the integral with respect to u. Okay, so the du.
oh yeah, no, I forgot. Okay, no, don't worry.
In this case, it's safe to think of it as just reminding you that this is with respect to u, not x or y or g or anything like that. Okay. That is our formula. Right. That's up here. Where did I put it? Way up here. The antiderivative. Okay. Remember what is an antiderivative? It's the function that when you take the derivative of it will give you the original function. So if you think about it, you take the derivative of this function, you're going to end up with a natural log of b in the top, and so you have to have something to cancel it. Okay, so this is going to be, I'm going to pull out the constant, which is 1 over natural log of 2, just so I don't have to deal with it. And then I'm going to plug in the top function. So we have 2 to the natural log of 3 plus 1, and then minus 2 to the 0. Okay, that's the fundamental theorem of calculus. So we have 1 over natural log of 2. What is 2 to the 0? Yep, it's 1. I'm just
One.
testing you with the basics here. Anything to the 0 is 1. So here, let me see, we can either leave it 2 to the natural log of 3 plus 1, or we can simplify a little bit. Using our rules for exponents, when we add exponents, it's part of the product rule. So this is the same thing as 2 to the natural log of 3 times 2 to the 1. Right? We can also write that way. It's the product rule, right? Okay, and that's kind of how I would leave it. I wouldn't leave it. I don't want to write 2 to the 1, but my answer then would be, simplest way of writing it, 2 times 2 to the natural log of 3 minus 1 over natural log of 2. There's a good way to write it. Questions?
Professor?
Yeah.
Will this answer look the same as if in the case we didn't change the upper and lower bounds and we just substituted back?
You would have the exact same answer.
Okay.
Let me do it that way. All right. Okay. So this way I change the bounds of integration. Let's say I didn't change the bounds of integration. Okay. Let me do it that way. What I would do is I would find the antiderivative of 2 to the u du. So this is alternate. I would find the antiderivative of 2 to the u du. We would still do the substitution, and we would get 2 to the u over the natural log of 2. But now let's resubstitute what we substituted originally, which was what? Natural log of x. Was that it? I forget now. Yeah, natural log of x. So instead of u, let's put it back in. 2 to the natural log of x over natural log of 2. Evaluated, now it's back in terms of x. We can evaluate it by the original the original number is 1 to 3e. Is that everybody clear what I'm doing? So instead of leaving it in terms of u and changing the bounds of integration, I'm putting, after I take the antiderivative, I'm putting it back in terms of x again. It is x, right? Yeah. And back in terms of x again, and now I can use the original bounds of integration, 1 and 3e. So let's see what that is. I'm going to pull out the constant, which is 1 over natural log of 2. And then I'm going to plug in my numbers. Natural log of 3e minus natural log of 1. It's exactly the same. As up here, we're just going to adjust it a little bit now. Same thing. Okay. So you can do it either way, whatever way you think is easier. Just be very clear and be very careful with your bounds of integration. If you're leaving it in terms of u, make sure you change the bounds of integration. If you're going back to x, make sure you use the original bounds of integration. So those are the 3 questions that were on the quiz. Does anybody have any specific questions from the homework or any other questions on this section? We're not taking a quiz today, remember? We're just going to review a bunch of problems. But I do want to leave time for inverse trig function.
Did you see my email? I sent you a couple of things.
I did. Were there some things from this chapter?
Yes.
Okay, I'll go check. Let me check here.
I can just tell you.
Okay, let me open up it's from the homework, right? So homework, so let's do homework 7.3.
So for 7.3, I have questions about problem 8, 12, 14, 15, and 19.
I have to say that one more time. I'm still opening up the
Okay.
the assignment here. Okay, I have it open. Tell me the first one.
8.
8. All right, let me look at 8. Okay, so 8. Okay, I don't want to devote too much time. I'm looking at the clock. I just want to make sure that we have time for the next section. We definitely want to do some practice with that. So this is a definite integral from 1/4 to 1/3 of 12 to the 1 over p squared dp. Okay, so what do you think would be the approach here? I know that we don't have this particular function in our list of integrals. It's not that easy. So what do you think would be the approach in general? Substitution. It's likely that it's going to be substitution. What do you think we might substitute? Look at this for an inside function. And if you can, look and see if that inside function that you're considering has its derivative also as a function, as a factor in here. But if not, just pick out an inside function and we'll try it out. P squared, we can try it.
1 over p.
1 over p, we can try that. Which one of you feel stronger about your suggestion?
I feel stronger, I feel like.
I think 1 over p.
Okay, so 1 over p. Let's try 1 over p just because the majority says it. Of course, if the majority says it, then it's always right. So u equals 1 over p. Remember, we can write that as p to the -1, just so we can, because I know we're going to take the derivative. So the differential equals the derivative of p to the -1, which is what?
P to the -2
P
dx.
to the -2
dx.
Over -2.
Be careful here. We're kind of mixing up the integral rules and the derivative rules. Here we're going to use the power rule for derivatives. When we take the derivative, we take the exponent and move it to the front.
-1 p.
Right. And then p to the, what do we do with the exponent?
0.
We either subtract 1 or we add 1. You subtract 1. With
0.
derivatives, you move the derivative to the front. You move the exponent to the front and you subtract 1 from the exponent. So it's -2, right? dp. And we can rewrite this as du equals -1 over p squared dp. Or another way to write this is negative dp over p squared. However you want to write it, this is all the same thing. Okay. Is this a good substitution? Looking back at our original integral, is this a good substitution? Here's our u.
It
Do we
is.
have a dp p over p squared? We sure do. The only thing that's throwing us off is what? What's the only difference?
The negative.
Negative.
We can easily move that over. In other words, multiply both sides of this thing over here by negative. So negative du equals dp over p squared. And so we have a perfect substitution there. So this is going to be equal to integral, and I'll deal with the bounds in a minute, 12 to the u. Instead of dp over p squared, it's going to be negative du. I'm going to put the du here, and I'll put the negative in front here. Now we just have to make a decision. Are we going to find the integral and then go back to p, or are we going to change the bounds of integration? What do you want to do?
I say keep it the same.
Keep it u?
That's what I prefer.
Okay, well, then you said it first, so that's what we'll do. We'll change the bounds of integration. We're going to leave it in terms of u and change the bounds of integration. So when t equals 1/4, what is u? I got to kind of look up here. U is 1 over p. So if p is 1/4, what's u?
4.
4, right? It's the reciprocal, 1 over p. And the same thing with the upper bound of integration. When p is 1/3, u is 3. Okay, so we're going from 4 to 3. This is a fairly simple one. Everybody okay with that? A question so far?
Oh, I was saying to not change the upper and lower bounds.
Oh, well, I already did it, so I
Yeah.
misunderstood you, so we'll continue this way. Because our substitution is that u equals 1 over p. Okay, so in other words, you plug in for p, you're plugging in 1/4, right? And that's a reciprocal function. U equals 1 over p is a reciprocal function, 1 over the other. Okay, there's another thing here that might maybe make this a little simpler. I don't know. Anybody know how we can get rid of that negative in this integral?
By flipping the 3 and 4.
Exactly. This is the same thing as positive integral from 3 to 4 of 12u. That's just a property of integrals. That if you switch the bounds of integration, it's the same thing as the negative of the integral. Okay, so there we are. This is nice to do. And this is a pretty easy antiderivative. What's the antiderivative of 12 to the u? That's right, it's itself divided by, that's right, natural log of 12. Good. Evaluated from 3 to 4. And I'm going to calculate that. I'm going to pull out the constant of the natural log of 12 and plug in my 4 and my 3. So 12 to the 4 minus 12 to the 3. And let me do this in my head. That's going to be 19,008 over, and we have our natural log of 12. And that's our answer. Violet, are you trying to ask a question? And does anyone have a question on this? Serene?
When you swapped the 3 and the 4
Uh-huh.
to make it positive, why
Uh-huh.
was that necessary?
It's not necessary.
Oh.
It's just I just like it.
Oh,
I just wanted to do it. You don't have to. If you had left it negative, it would turn out to be the same exact thing.
can you scroll to the, yeah. Never mind.
Violet, are you there trying to say something? I can't hear you. Okay, but Violet, you had another number though. If you want to type in the number of the next problem, we can look at. I'm going to give it just, we have to basically choose wisely, choose one more, because we have to move on to the next section. I want to take a 5-minute break. So choose one more really difficult one.
Question 12.
12, okay, that's,
Is it difficult? If it's not, then let's just do something else.
it's, okay, it's kind of nasty. Let's take a look at it.
Okay.
All right, so let me see. We have a function f of x equals the sine of x. This is a good one. We haven't talked about this yet. To the exponent of the natural log of 12x. I'm going to leave it at that for now. They also want you to evaluate it, but that's just a matter of plugging in a number. So let's just look at the derivative of this. We call this a tower function. Hopefully you read that in the text or saw it in the videos. The tower function means we have a base that's a function to a function. It's a function to a function. And actually this function here, f of x equals x to the x, got me fired from a job because I was working on it and the owner of the company networked in and saw that I wasn't doing my work. I was doing this. So I'll never forget that one. But I still like them. So a tower function, we basically are taking advantage of our definition of base other than e. In other words, b to the x equals e to the x times natural log of b. You remember that definition? So that's what we're going to do. We're going to rewrite this function in this way, where what would be our b here in this case?
Sine of x.
Yeah, the base here is this. So this would be our b. Okay. So let's rewrite this. This is going to be equal to, I'm going to call it y, just to make life easy. Y equals e to the x natural log of our base, which is sine of x. Yeah, what did I leave out? Right, it is not just x, it is natural log. Yes, you're absolutely right. Move this over. E to the natural log of 12x times the natural log of sine of x. Does that look right? Natural log. Base, we have our base. Okay, let's give this a try then. All right, so the derivative here with respect to x is going to be, well, this is base e. So what is how do we do the derivative of base e?
It's the
Yeah, the
same
derivative
thing.
of an, it's right, it's itself. So I'm going to write e to the natural log of 12x times natural log of sine of x times, because this is a chain rule or a composite function, times the derivative of what's in the exponent. This is just I was going to say simple, but it's a direct use of the product rule, right? We have a product. So it's going to be the product, the derivative of the first one. Put this in parentheses. Derivative of natural log of 12x is what? Yeah,
12x.
it's 1 over 12x, and then what though?
Times 12.
Times 12, right? So they cancel out, and we end up with just 1 over x. It's that case with all natural logs like that. So the natural log of 80x is going to be 1 over x. Okay. Times the other function, which is the natural log of the sine of x. Then plus the first function, I'm running out of room here, natural log of 12x times the derivative. Let me shrink this a little bit here. Oops. Okay, times the, let me see, where am I? Okay, times the thing, times the derivative natural log of sine of x. What's the derivative of the natural log of sine of x? Well,
1 over sine of x
1 over, okay, so 1 over the argument, 1 over sine of x,
times the derivative of sine of x, which is cosine of x.
which is cosine of x, right? That's why I left a little room in the top. Okay. So I think that should be what we're looking at. So what is, how can we simplify this? This is the answer, but I don't want to leave it like this. This can definitely be simplified. First of all, what is all this? I can write this in a slightly different way. Where did I get that from?
You can change the bases now, so it can be sine of x
Yes.
raised to the ln of 12x.
Yes, exactly. In other words, this is our original function. I changed it to e to all of that because that was the way we could take the derivative here. But we can now go back to the original function, sine of x to the natural log of 12x. So let's do that first. So the derivative equals, my memory is sine of x, sine of x to the natural log of 12x. Okay, so that's what's in blue there. We're going back to its original form. And this one is just a matter of adding those together. So this, first of all, how can we change, what can I write here? Instead of cosine of x over sine of x?
Cotangent.
Cotangent, right? That's an easier thing. One function is easier than two. So that's cotangent. Cotangent of x. And other than that, I'm just going to add them together. So I have natural log of the sine of x plus x times natural log of 12x times cotangent of x all over x. And there's your answer. I'd like you to change the cosine over sine to cotangent of x, but I would probably not take off any points if you left it.
Wait, Professor, I have a question.
Yes, yeah.
The one, why is everything over x? Wouldn't it just apply to the first?
I wanted
Yeah,
to
was
add
gonna
them
ask
together.
that.
I wanted to add these two terms together, this term and this term.
Oh, so you just added an x.
Right, I took the least
Right.
common denominator, which was x, and I multiplied the second term by an x. That's right here. If you notice, that appeared there.
Oh, I see it. Yeah.
Okay,
Okay.
so I'm just gonna repeat that. So something like, if we had 3 over x plus 2, and when I add those together, it would be 3 plus 2x over x. Right, I would multiply this by x over x. So they both have the same denominator.
Would there be an issue if we just kind of left it as ln of sine x over x
Well,
plus?
like I was saying a minute ago, as long as I want to see this changed back. I want to see that you recognize that this is our original function, but I wouldn't have a problem with you leaving this not added together. If you just had 1 over x times the natural log of sine of x plus natural log of 12x cotangent of x. It would be okay to do it that way.
Okay.
Okay, but I do
Professor?
want to see that you recognize that this is your original function. All right, yeah, go ahead, ask your question.
I was just gonna say, like, you know how I said to do it with the different, without changing the bounds? I was doing it by myself just really quickly, but I didn't know how to get rid of the negative.
The negative.
So I'm not sure if I ended up with the right answer, basically.
Let me see. Where is the negative? What you're talking about another problem?
Yeah, the previous problem I
Oh.
was saying.
Well, the negative, I can tell you here, if you left the negative here, you don't reduce the bounds, then it would be from 4 to 3, and so these would be switched, and therefore the sign would be switched, which would take care of the negative in the front. It would be it should be the exact same answer anyway.
Okay.
Okay.
So if I didn't change
let's take a quick break. We'll come back in 5 minutes, all right? And then we're going to work on the other section, on the last section here. I want to make sure we have time. Okay, I'll see you in 5. I guess that was 5 minutes. All right. Let's go on to the last section of the entire semester. Section 7.5, and this is has to do with inverse trigonometric functions. With these, they can look kind of complicated. The best thing to do is to get used to looking at them, identifying them as the function that they are, and appropriately plugging in. Now, you're going to have all these formulas, these derivatives and integrals on the test with you, but you want to practice doing them ahead of time. If you wait till the test, it's not going to give you the answer that way. You have to be careful and methodical with these. But on the screen are the formulas for the derivatives on the top, and then formulas for the antiderivatives or the integrals up here. First, I'm going to go through the 3 quiz questions, and then we'll go over any other. I'm sorry. I see 3. 7.5. We'll do more than 3, but okay. So let's take a look at the first one. And again, I have to say that the big thing here still has to do with substitution, and but there's a little bit of finessing to do here. So let's look at the first problem. We're given f of y equals the inverse tangent. Okay, remember, that's what that -1 exponent means. It's not an exponent. It's a symbol that means the inverse tangent of 6y squared plus 7. We can also write this as the arctan, the arctangent of 6y squared plus 7. It doesn't matter which one you write. It's just a different symbol. I usually write tan with the -1 there. And we're finding the derivative of this. So I'm going to look at my functions. Up at the top left, I see that the derivative of the inverse tangent function is right here. That's what we're going to use. It is, of course, not just an x that's in there. It's in this case, it's a y. It's not just a function. It's not just y. It's a function of y. So what rule do we have to also apply here? Not substitution. We have a function, instead of just the inverse tangent of y, we have the inverse tangent of, and then it's a whole function. So what is it? What rule is it? What's the word I'm looking for? It is a composite function. And so when we have a composite function, what derivative rule do we use?
The chain
Not
rule?
product, chain rule, right? Product would be if it's a product. This one is not a product. It isn't a composite function, and we're going to use the chain rule, which means we take the derivative of the outside function, which we have right up there, the derivative of the tangent, inverse tangent, and then we multiply it by the derivative of the inside function, which is actually the easy part, okay? So the derivative, well, is right up there. It's 1 over 1 plus, instead of x, it's going to be this entire argument, 6y squared plus 7 squared. Okay. And then times the derivative of the inside function. The derivative of 6y squared plus 7 is
12y.
12y, which I put in the numerator. Okay. So there's our answer. I think we should do a little bit of simplifying here. Leave the 12y on top, 1 plus, and then expand that, which would be 36y to the 4th plus 7 times 6 is 42, 80, 4y squared plus 49. And finally, I'm going to add the 1 and the 49 together, so we have our answer is 12y over 36y to the 4th plus 84y squared plus 50. And there's our answer.
Professor,
Yeah.
Professor, would you have an issue with us leaving it with 1 plus 6y squared plus 7?
You know,
Raised to
with
the second
these
power?
with these questions, I know that they're kind of, they can be scary looking and daunting. If you got as far as writing it this, I can't believe that I would be that heartless to take off any points. Some of you might disagree. I care, but because I'm a chill teacher, I would probably leave it there. All right, I'm gonna ask you to sign a document that says I said. Questions on this one? I did, no, it's true. I was right before this class. I have their phone number too. They weren't smart enough to block the phone number, so I'm gonna call them after this class and say we got disconnected. And I'd like to discuss it further. I will. Oh, I will. I don't let things go. My brother teaches English. He says I hold on to things like grim death. All right. Let's look at number 2. We have an indefinite integral 2 over square root of 49 minus x squared dx. And we're going to find the integral here. So we're going to use, we have our table up here. Let me copy this and put it over here so we can look at it. So you have to recognize this. Well, the one thing, on the final exam, you're not going to necessarily know that this is going to result in an inverse trig function. So be very careful. You might look at this first and think maybe substitution. If you try, your substitution would probably leave you short. You'd end up having a negative 2x or so, an x in the numerator, which we don't have, and it would end up being a mess. So you want to recognize that this is something appropriate to use one of these 3 formulas for. So looking at the ones on the right, which one is the closest? Which structure? Which one?
Sine.
The first one,
Arc
because if you look at it, the a, of course, is a constant. So we have 1 over the square root. That looks good, except for the 2. Remember, we don't care about a factor of some constant. We have a square of a constant. Minus x squared. So it does look like number 1 would be the appropriate choice here. So we just have to make sure we label everything. A squared, what is our a in this case? 7,
A
right? So
squared is
it
40.
might help to just rewrite this like this. As a matter of fact, I want to look as close as I can to the original. So I'm going to pull that constant of 2 out, right, from the numerator, and I'm going to put that dx in the numerator, just rewriting it a little bit so it looks more like that one. And then square root of 7 squared minus x squared. That makes it look a lot better, right? So I know my a equals 7 in this case. I don't have to do a substitution with the x squared because it's just x squared down there. Okay. Everybody good with that so far? All right, so now we take the antiderivative. We're looking over to the right, what our provided formula. Well, it's going to be the arc sine, or the inverse sine of, in this case, it's just x over a, which is 7, plus c. What did I forget? I forgot something here. Yeah.
Why would derivative of inside function?
Well, no, the only thing I'm missing here is the 2 that I had out in front. Other than that, this is it. My x didn't have to be changed anyway because it's just x. My a squared it turns out to be 7 squared. So instead of the a, I use a 7. Other than that, this is it. So there's the answer. 2 times the inverse sine of x over 7 plus c. Questions on that one? Let's look at the last one on the quiz. And we have the indefinite integral dy over y squared minus 8y plus 32. Okay. So again, we could try a substitution. It's not likely going to work. I hope, on this test, on this upcoming test, I hope to go pretty much straight to these inverse trig functions. On the final exam, you have to be, you might be tempted. You don't know if it's right. So after you exhaust all your other options, you might say, all right, maybe this is something like one of these. Which one do you think we're going to look at for this one? Which is the most like it?
Number 3.
Well, number 3, do we have a square root in the denominator? We don't have a square root in the denominator. So that would for me, it would eliminate number 1 and 3. We
Like
don't have
open-
a binomial in the denominator, but we can fix that. We know our pre-algebra, and we can make a trinomial into a binomial. Okay, so to me, it looks mostly like this, mainly because we don't have we have a y squared in the denominator, and we don't have an x a radical. So how do we do that? What can we do to this denominator here to make that look more like this over here?
We can turn it into y minus 4 squared plus 16.
Y minus 4 squared plus 6. That sounds right. So
Yeah.
how did you do that? What's the method you used?
So we would complete the square.
Completing the square. Exactly right. So we're going to complete the square for this denominator here. So we have y squared minus 8y plus something plus 32. Okay. And remember, when we're completing the square, we're going to add something here that makes this a perfect square trinomial. What number do we add there? Well, we look at this middle here, the -8, and we divide it by 2 and we square it. Half of -8 is -4 squared is 16. So we add 16. If we add 16, we also have to subtract 16. We can't just change it, but we can change the structure of it. So I add 16 and I subtract 16. Now this in the parentheses is a perfect square trinomial, which simplifies to y minus 4 squared. Then we have 32 minus 16, which is plus 16. Okay, we now have two terms, which looks a lot more like what we want it to look like. So I'm going to say that this now equals dy over y minus 4 squared plus 16, but it doesn't look exactly like I want it to look. As a matter of fact, let me draw it. Let me write it backwards just because so it looks more like what we have up there. So I'm going to write the number first. So 16 plus y minus 4 squared. Okay. All right. So I still want to look at this. So I want to have it look more like that. So what would my A be in this case?
4.
It would be 4, right? Because I could actually write this 16 as 4 squared, which I want to do. So A is 4. Let's make, because we have a y minus 4 squared, let's do a substitution here. Let's say let x equal y minus 4. Okay. And the differential dx equals the derivative of y minus 4, which is just 1 times dy. So I can substitute that up here, and I can substitute my x for down here. So I now have x over, I'm going to say a squared plus x squared. Is everybody okay with how I did that? Our A, I think everybody's okay with the A. Annabelle, you got a question?
Yeah, could you explain what you wrote in blue? Because I really did not follow how you.
As far as the completing the square?
Yeah.
Completing the square. Yeah, let me see. So if we complete the square, as long as you can do anything you want as long as it turns out to look like what we're looking for in the formula. 1 over some constant squared plus some function of y squared. So to complete the square, we have, let's say we have x squared plus 3x plus 1. And I want to complete the square here. I am going to look at this part here. So I have x squared plus 3x. And I'm going to add half of this. And I have the 1 out here. So I take the 3, I divide it by 2, and I square it. Okay, which gives me 9/4 in this case. So that's what I add, 9/4. Since I add 9/4, I subtract 9/4. This is the method that you're going to use to complete the square, no matter what you have there. This now factors. It's a perfect square trinomial. So this is x plus 3/2 squared. And then 1 minus 9/4, 4/4 minus 9/4 is -5/4. So minus 5/4. I hope I did that right. 4 minus 9. Okay, that's how I complete the square. Yes. Yes.
Should we always choose to complete the square in this situation?
In this situation, this is the best method. Yes.
Is there any other method or no?
I never used another method.
Oh, okay.
Because we want to have it look like exactly like this with a function of x squared and a number squared. You know, if we're starting with a trinomial, this is kind of the best way to do it. I hear you resisting it. You don't want to do it, but write down. You're allowed to have a note card with you. Make this, put in little tiny letters an example of how you complete the square. Okay. All right, so let's now scroll up. All right, so now I'm going to find the antiderivative, which I get from up here. It's 1 over a. Let me again make one more copy of this. Okay, so working over here, we have this equals 1 over a. What's our a? Our a is 4. So 1 over 4 times the inverse tangent of x over a. Okay, x over 4 plus c. However, remember x is a substitution. What is our actual x? It's y minus 4. So I'm going to replace the x with our original y minus 4. And there's our answer.
Professor? Professor?
Okay, so be careful with your substitutions. Be careful. Try to, with these, you want to make it look as close as you can to, to the function that is in the formula sheet. Wait, how would we check to see if this is the correct answer in this case, if we wanted to check? How do we know if any antiderivative is the correct one?
We take the derivative.
Oh, okay. Anybody trying to talk? I had you muted.
Yes. I was gonna ask, what if we made the y minus 4 squared the a and the 4 the x?
Well, you can't because a stands for a constant, no
Oh,
variables.
okay. Gotcha.
Okay, so you've got to be careful. In this case, with you can't. You don't want to do that because you'd end up with 1 over x times tan inverse
Yeah.
tan. That wouldn't be correct. Yeah.
Okay.
So remember that the a's are always some constant. Yeah.
Okay, that makes sense. Thanks.
All right. We have other problems in this. Now I know, Violet, you sent me a more of a list on these. Do we want to see some of those problems?
I also send you a
No. You said you want a quiz? What? Oh. All right. Well, let me look at the homework for this section. Daria, or was it Daria? Do I keep asking you, Violet, and it was Daria?
It's that, yeah, it was Daria.
Oh, I'm
So
sorry.
I have a question about problems 15 and 16, 7.5 homework.
Okay. I'm sorry for confusing. 15 and 16? The last two?
Yes, yes.
All right, let's take a look. Okay.
Actually, we just did 16, so let's just do 15.
Okay, okay. Let's look at number 15. So this is 15 in the homework, 7.5, 15. We have a definite integral from 1 to the square root of e dx over x times the square root of 1 minus natural log of x squared. This is a good one. I like this one. Okay, so if you're looking at these formulas here over on the right, you might be a little tempted to look at number 3. Do you see why that might be a temptation? Well, I see what's a temptation. We have a radical in the denominator, and we have an x in the denominator. What's different, though, about these two? That's right. It's the function of the x is minus. It's the second term. It's minus natural log of x. In the number 3 example, we have x squared minus the constant, and that makes a difference to have a negative there. So it might not be that one. So what could we do? Anybody have an idea of how we could approach this one? What method we could use to start it?
It could be cosecant, because if we the other option for secant is just a negative. So if you apply
Right,
a
well-
negative,
Well, it's not a negative outside, it's a negative within the radical. And I can tell you that that's going to make it it's going to make it so it doesn't work. It's none of them yet. Okay, so there's something else we actually have to do here. And I'll tell you, it's going to be substitution. All right. What could we substitute in here? Think of give a guess. Somebody give me a good guess for substitution. Let u equal what?
1 minus the square root of the whatever's inside the radical.
So 1 minus natural log of x squared. Let's give it a try. Then the differential of u would be equal to -2 natural log of x over x. Does that help us? Do we have an x in the denominator? Do we have a natural log of x in the numerator? So that's not exactly good. That's a reasonable guess. Whoever said that, that's not a bad guess. But it doesn't work so well because we don't have a natural log of x in the numerator. Can we think of and try another one? And like I said, some of these it's trial and error. What other inside function could we try? Minus what? Of the logarithm? You're not committing yourself here. 1 over x, but yeah, you could do 1 over x, but then what would be, we write that as x to the negative 1. What would be the derivative of the differential? -1 over x squared. That doesn't really help us. What did you say? Natural log of what? We don't, not natural log of 2. That's actually a natural log of x squared. I'm gonna listen to the person in the back row who is saying natural log of x. Okay, let's try that. Natural log of x. What would be the differential? What's the derivative of the natural log of x? 1 over x times dx. Do we have that? That's exactly what we have. So that's a good fit. Person in the back row. Okay. This one is a little bit of a trial and error. But this one works. So if you substitute natural log of x, we have a perfect substitution. So let's try that. This equals, instead of dx over x, we're going to put du. Instead of natural log of x, we have u. So we have square root of 1 minus u squared. This does look like what? Which one does this look like? It looks like 1.
The first one.
Okay. It's in exactly the shape of that 1 is. So we don't have to do very much here. The only thing we have to make a decision about is the bounds of integration. Do we want to change the bounds of integration or do we not?
No.
No. Okay, that's a definite no this time. Let's find the antiderivative and then put it back in terms of x, and then we'll evaluate. So what is the antiderivative here? We know it's number 1. So what would be the antiderivative?
Arc sine of x over, well, in this case, u over a.
U over a. What's our
Plus-
a?
A is 1.
It is 1. So just u,
U.
right? Arc sine of u over 1. But we don't have to write that. Does that look good?
Yep.
Okay. Everybody get that? And this we're now going to write it back in terms of x, because I received the message that we want to do it that way this time. And so instead of converting the bounds of integration, I'm going to say that this is the inverse sine of, instead of
Wait,
u.
Professor,
Yeah,
I was gonna say you didn't write the definite symbol thing.
you mean the
because
bounds
this
of
is a definite
integration?
integral. Yeah, the bounds of integration.
Well, because I didn't want to convert. I was given orders not to convert the bounds of integration to terms of
Oh
u.
yeah.
So I'm waiting to do it until we go back into terms of x.
Okay.
And now we're back in terms of x again. And I'm going to use the original bounds of integration from 1 to square root of e. Okay. We could have converted the bounds of integration and then put them right here and gone straight to it. But in this case, we're trying it this way. It's going to give us the same answer. So this is going to be equal to inverse sine or arc sine of the natural log of square root of e minus the inverse sine of the natural log of 1. Everybody good so far? All right, so to figure these out, I'm going to be looking for exact answers here. I'm not going to be accepting calculator approximations. In other words, don't put this into your calculator. Figure it out. You will also be given on the test the basic trig values and all that. So use them, and also use the properties of logarithms and all that. Let's simplify this so we can deal with it. Inverse sine of, what is the natural log of square root of e? How else can we write that? That simplifies to something. This is just rules of properties of logarithms here.
Would it be the natural logarithm of e to the power of 1/2?
That's a way to write it, and I prefer it that way. So instead of square root of e, it's e to the 1/2. Okay, let's keep working on this first term, and then we'll deal with the second term. Now, what else can we do with that?
You bring the 1/2 to
You can
in
bring
front
the
of
1/2 down to the front, and you're left with natural log of e. Okay. What we can do? We can simplify further. It's just right. It's just 1/2. Why is it 1/2? What is the natural log of e? 1. So this is just the inverse sine of 1/2. Okay, that wasn't calculus. That's just rewriting this. So the natural log of square root of e is 1/2. Minus, let's start up here. The inverse sine of, what is the natural log of 1?
0.
It's 0. All right, so I'm going to go right down here. So that's minus inverse sine of 0. Now we can calculate these. What is the inverse sine of 1/2? Do we know what that means? Do we remember what these means? The inverse sine?
Pi over 6.
It's pi over 6.
Mhm.
Yes. In other words, it's the angle that when you take the sine of it in the restricted domain, that gives us 1/2. And so, yes, that is pi over 6. That's the angle. What about the sine, the inverse sine of 0? What angle when we plug it into sine gives us 0?
0.
0. So our answer is pi over 6. Wasn't that fun? No. Okay. Questions on that? Change the bounds of integration? Yeah, sure. I'm going to do the same thing, but I will change the bounds of integration this time. So that means we got to go back to here. So from 1 to square root of a. Okay. All right, so I'm going to leave it in terms of u. And I'm going to change the bounds of integration. And to do that, I have to go back up here. So let me copy this. Okay, so when x equals 1, we need to figure out what u equals, and then when x equals square root of e, we have to figure out what u is. So when x is 1, What is u? It's 0, right? How do we know that? Well, we go up here. Here's our relationship between u and x. We plug in 1 for x, so natural log of 1 is 0. So u is 0. That's the lower bound of integration. What about when x is square root of e? We have the natural log of square root of e, which is, for the same reason we discussed above, 1/2. Where's 7u? That sounds like like my bad handwriting. Where? Oh, right here. Yeah, that's my bad handwriting. It's an arrow. Same thing up here. Sorry. Okay. A number of times on people's exams, I've said don't use arrows instead of equal signs. They're not the same thing. So this means if x equals 1, then therefore u equals 0. Okay. So in this case, what did I say this was? Square root, it's 1/2. So that's our bounds of integration. And we now no longer have to plug back in the natural log of x. So we just have the inverse sine of u from 0 to 1/2, which is, as we know, inverse sine of 1/2 minus the inverse sine of 0, which we know is pi over 6 plus 0 or pi over 6. I prefer to do that way, but I don't know if it's easier. I'm not really sure if it's always easier. It's easier. Okay. Okay, we have 10 minutes left. Tell me what you want to look at here. I'm looking through the homework. Maybe let me do one more that's a little more difficult. All right, let's try. That's the symbol for the inverse sine. That's, well, I'll only show you why. Right here. Those are our formulas. When you have, it's number 1. We have dx over square root of some constant squared minus x squared. So we're just plugging it in, and that gives us our answer. Okay. Let me do one more here. And this is from the homework number 14, 7514, 714. So we have the indefinite integral of 8 over 49 x squared plus 81 dx. All right, what do you think we should do here? What does this look like? Let me once again try to get our it does look like number 2. Okay. Because there's no radicals there. So that pretty much tells me that's what it's going to be. So I might have to really play around with this though, because I want it in terms of just an x squared and a constant squared. I'm going to first pull out that constant of 8. So it looks a little bit better. I now want just x squared. I don't want 49 there, because if you look at this, it does not have a constant there. It has to have just x squared. So how do I get rid of that? That's right, I factor it out. Okay. Good suggestion. So I have 8 dx over. I'm going to factor out the 49. What do I have left inside? If I factor out the 49, I can't just factor it out from just the x squared. I have to factor it out from the whole expression in the denominator. So what's left inside? X squared plus what? No, this is not just 81. We had to factor out a 49 from that. We factored out a 49 from the 81, so we're left with 81 over 49. Yes.
Professor?
Hold on. Say keep going.
7x squared, whole squared, plus 9 squared, and then we apply directly number 2.
Well, the number 2 wouldn't be direct, because we don't have a squared plus c squared x squared. In other words, we don't have that x multiplied by a constant there. in number 2.
There is a
Professor?
No, I mean, in the formula, so we have to make it look like that formula. It's a constant squared plus just x squared. Follow what I'm doing here. It works. So I'm going to continue, and what I'm going to do here is I'm going to factor out. I'm going to pull that 49 out of the integral. Also, it's just a constant. So we have 8 over 49 in the out in front, dx over x squared plus. Now, I'd like to write that in terms of a constant squared. So what is 81 over 49 in terms of what squared, something squared? Right, 9 over 7 all squared. Now it looks like that function. Okay. So we can now take the antiderivative. I have my 8 over 49 times, what is the antiderivative? It is 1 over a. What is my a in this case? 9 over 7.
9
So what
over
is 1
7.
over 9 over 7? How can I
7
write
over
that
9.
better? I'll do it twice. 1 over 9, 7 times the inverse tangent of x over a times the inverse tangent of x over a, and our a is 9/7 plus c. All right. I don't want to leave it like that. Those are complex fractions, and I don't like that. So I'm going to rewrite that. The only thing we have to do here is this and this to kind of even that out. So how do we do that? 1 over a fraction is the reciprocal of the fraction. So this is 8 over 49 times 7/9 times the inverse tangent of 7x over 9. Same thing on the inside. Come on. 1 over a fraction is the same thing as the reciprocal of a fraction. And here we can simplify this. 7 over 49 is 1 over 7. So we end up having 8 over 63 inverse tangent of 7x over 9 plus c. There's our answer.
Professor?
Questions on anything
Yes.
in the universe?
Can you hear me?
They're talking. Oh, it's a lot easier when I mute people. I have less questions. I'm sorry. So what were you saying?
At the top, couldn't we just have done, rather than like right there, where it says 49x squared plus 81, before you did the taking out the 49, couldn't we have just put 7x and then put that in parentheses squared plus 9 squared?
You might be able to, but then you're going to have to do a substitution. Because up here, this doesn't have a constant times x squared. It's just x squared. That's why I wanted to pull it away. So I just have the x squared. If you leave that 49x squared, you would have to do a substitution to get rid of that. Or let's say 7x squared, and let 7x be u equals 7x. So differential of u equals 7 dx, and then 1/7 du equals dx, and do it that way, and it might work also.
Okay, gotcha.
Okay, with math, there's usually more than one way to do it. I would suggest doing it my way only because it's written down nicely.
Yeah.
And that was my first instinct, was to just the most direct way to make it look like that function. But what I'm saying is, if you do something a different way, if it's mathematically correct and you do it correctly, I'm not going to object to that, in terms of this kind of thing.
Gotcha.
I did it with substitution and it looks correct. I got the same answer.
Okay, yeah, I mean, like I said, if as long as you're doing mathematically correct things, you'll get the same answer. So you can do a substitution there if you want to. We're running out of time. Let me think of any general things. The exam will be open tonight as usual at midnight. I'm going to ask those of you who are doing remote to be extra careful here. I hate to say this, but I've found 3 people cheating in the last week on remote exams. I'm either getting better at detecting it or it's just happening more. I think so that happens. Desperation sets in. Don't do that. And what I'm going to ask you to do is please be very careful that your room is well lit, that I can see you, that I can see your entire desk. Some of you I've been kind of letting it get away where I can only see your backs. Don't do that. Make sure that I can see your entire desk well lit, and your answers that you put up, that you send to me, make them clear, make them well lit also, so I can clearly see your answers. If you have any questions, you can send them to me. I will send you an answer. I will send you a video. I have some examples already done that I can send you. So, study hard. And I'll see those of you who are going to be taking the final exam on Wednesday. I'm going to grade as fast as I can your other exam, but you might, some of you, I think it'll be obvious to you that you don't have to take the final exam if you don't want to. But I think a lot of you are going to want to do that because you're going to, you're on the edge, or you want to raise your average or take a chance on it. So anyway, all right, that's enough talking. Any questions about anything at all in the universe? All right, then go home and good luck, and let me email me if you have any questions.
Thank you, Professor.
Thank you. Enjoy your.
you.